Hi guys, Dr. J here, and in this video we're going to talk about a couple of quick definitions, and the first one is the divergence theorem. So divergence theorem is very important. It says that the integral over a volume of the divergence of a vector field F. Let's talk about what this is. So integral over the surface of that field dotted into the normal times the surface increment. So what does this mean? We have a volume and we have some field which is passing through the volume. Think gravity, think magnetics. So some volume, there's a field passing through that volume. This actually is a very important law for many other physical phenomena as well. But for us, we have a field passing through the volume, and the divergence of that field integrated over the total volume is equal to the field dotted into the unit normal n. Here, if you have some line, the unit normal is just a small arrow. Sorry, that's a little small. Let me make that bigger. There we go. It's the unit normal. It's a unit vector, so a vector with a length of 1 that's pointing exactly perpendicular to a surface. And so what this is saying is if we take the total divergence in this field, in this volume, and maybe I can just draw a little volume here, then that divergence integrated over the whole volume is equal to the field times the normal vector that's just on the surface times the surface increment. So we're basically going to integrate over the surface of this thing and get the component of the field which is parallel to them. So remember, this is a dot product here. Both our field and our unit normal are vectors. So we take a dot product of two vectors. That gives us a number. And we're going to integrate that number over the surface of our volume. Here we have our divergence, del dot F. So that's also a number. We're going to integrate that number over the volume. What does this mean? Well, basically what it means is that if something's coming into a volume and then something's leaving a volume, the difference between those, the net change, is going to equal the divergence. And so if you have this field and it's kind of moving through this volume, whatever's inside the volume needs to match whatever's coming in plus whatever's going out, or I guess minus whatever's going out. This divergence theorem actually applies to fluid flow as well. So for example, if you have fluids moving through a volume, this divergence term, if you just have fluids moving through, the divergence term would have to equal 0 because what's coming in is equal to what's coming out. If you have this term is not equal to 0, then you have some kind of source. Maybe you actually have a mass inside of the volume. Maybe the volume itself is a mass. And so that would be a source term. And so the divergence, then there's going to be a difference between what's coming in and what's going out. And the difference is going to be the source inside of that volume. So if there's no sources in the volume, then what's coming in must equal what's coming out. And that's basically what this is saying. So if you were to take this field, how much is moving in and out through the entire surface, the entire boundary of the volume, what's moving in and out through the entire surface, over the entire surface of this volume, it's got to match whatever change is happening inside the volume, right? So if we're getting, we have not talked in detail yet about the gravity field or the magnetic field. But basically, if there's no gravity, if there's no mass inside this volume, then what's coming in, the field lines coming in, has got to equal what's coming out. That's basically what the divergence theorem says. Okay, so divergence theorem, very important. We can use this actually to prove a lot of different identities and things. Integral over the volume of the divergence is going to equal the integral over the surface of the field dotted into the unit normal, integrated over the surface of this volume. So change over the volume, what's coming in minus what's coming out, has got to equal the change inside the volume, which is the divergence, which is having to do with whether or not there are sources in the volume. Hopefully that makes sense. I know divergence theorem is one that's a little bit abstract, a little hard to understand maybe first time around. Hopefully as we get into more concrete examples with the gravity and magnetic fields, it'll make more sense. Another one I want to introduce is the Stokes Theorem. Now, Stokes Theorem is not quite as important probably for us as the Divergence Theorem, but still pretty important. Stokes Theorem is going to say something sort of similar. It's going to have a similar form to the Divergence Theorem in that we're going to have a surface integral, and that's going to equal something else. But the something else is not a volume integral now. It's actually a line integral. So what this is saying is that the integral over the surface of some, again, we're sort of thinking about some volume here. We've got, some volume. Sorry, I didn't draw that very well. Some volume, there's going to be a field, again, our vector field f, and really the gradient operator here is a vector as well, so I should probably write that down. Make sure all my vectors are denoted as such. So the curl now, remember, grad or del cross f, that's the curl of that vector field. We integrate that over the surface. That is going to equal an integral around the integral around the area. So if we have a bounding surface or bounding line, really is what this means, it's a line integral. We integrate that field over that line. What this basically says is we're going to get the same number. So what Stokes Theorem is saying is if we have some volume, or really I should say some surface, and let me again just draw kind of a random surface here, the integral of the curl, that's our curl of f, over this surface is going to equal the line integral or the path integral around the edge of the surface. So if we take this integral, we integrate, if we have some field, and I'll try and kind of draw this here. Some field f that's passing through the surface. We take the curl of that field, we integrate that over this whole surface. That's going to equal the line integral around the edge. So if we call this C, we've got a line kind of covering the edge of the surface. We can integrate the field around the edges. So again, sort of similar to the divergence theorem. We can integrate around those edges, little line segments, dl. So those are line segments. And then we get the same thing. So we can integrate f just around the edges, or we can integrate over the whole surface. Now you might say with both the divergence theorem and the Stokes theorem, like how does this really help us? Do we still have to do an integral in either case? We still need to know what f is in either case. How does this make things easier? What it's going to turn out is because these are sort of about the boundaries, so surfaces, lines around the edge of a surface. Because these are going to be focused on the boundaries, we're going to be able to do these integrals a lot easier when it comes time to actually looking at gravity data. Okay, so that's Stokes theorem and divergence theorem. Let's do a couple more real quick. Okay, so there are several identities in the book called Green's identities, and we're going to use those identities to prove some things. I don't want to spend a whole lot of time about them, just sort of present them to you, and then there'll probably be some things in the book eventually where we ask some questions about it. But we're going to keep these at a bit of a high level. It is a little bit complicated in math, but I want you to get used to kind of looking at these things and understanding, okay, what's a volume integral, what's a surface integral, what's a line integral, and how are these things are going to work. The more comfortable you can get with this math now, the more the gravity and magnetic derivations that we're going to do coming up very soon, they're going to make more sense. Okay, so this is kind of based on the divergence theorem. We have an integral over a volume of u del squared v. So I have u and v here. I should probably use something different. Let me change v to w, just so it's a little easier to see. There we go. I think I got all the spots. So u del squared, del here, that's our null operator, or del operator, sometimes we say. So del squared w, that is something that I haven't mentioned yet. That is the Laplacian of w. So del dot grad w is equal to del squared w. So it's the divergence of the gradient. Divergence of the gradient is what we call the Laplacian. You can think about the Laplacian as like a second derivative operator, but in multiple dimensions. So we have u times the Laplacian of w plus gradient of u times the gradient of w, and we're going to integrate this over the whole volume, and then that's going to equal a surface integral of just u times the derivative of w with respect to n, and n is our unit normal. So what is this here? So we have this whole complicated thing that's going to be equal to a surface integral of one of our fields. So these are like two fields. You can think about them that way. Or in some cases, one might be a derivative of another one. But they're somehow two kind of vector fields. We have one here, u, and then we have the derivative of the other one with respect to n. N is, again, our unit normal. So it's the line, it's a unit vector which is perpendicular to a surface. So we have this surface. Again, maybe we have some volume and it has a surface. That surface has a perpendicular to that. That is our unit normal. So we're going to integrate over that surface. We're going to take the partial derivative of w with respect to that normal. And then we're going to multiply that by our other field u and integrate that over the surface. That's going to give us the same thing as this top quantity here. Again, I'm not going to go into a super lot of detail. You can kind of see how this is coming from the divergence theorem. We have a volume integral and a surface integral, and this is going to be just a useful theorem for us later on. So just introducing that. That's Green's first identity. Before I jump on to Green's second identity, let me just say, what is one place where this comes up? Well, that's if w is equal to u. And so if w is equal to u, this simplifies down quite a bit. We get a volume integral u, Laplacian u, Laplacian u, gradient of u squared, dv. And then we have the same thing on the other side there. There's u, and then the gradient of u with respect to n. It turns out that if this is harmonic, we're going to define harmonic in another lecture. But if this is harmonic, which it's going to turn out that that is the case for certain potential fields like gravity, and then this is equal to 0. So then this thing goes away. Then if we assume that u is also 0 on the surface, so if u is harmonic, that means the Laplacian disappears. If u is 0 at the surface, then this integral over the surface disappears. And then that means that the integral of this gradient over the volume equals 0. That actually has to vanish everywhere. So this has to be equal to 0 everywhere if this integral is, because this is squared, right? So if it's anything other than 0, then you would end up with a positive quantity here. You integrate that, you would get a positive quantity. And so this must equal 0 now everywhere inside this volume. Okay, so now let's introduce Green's second identity. And this is going to be another integral over a volume. So what do we have? We have an integral over a volume, u times Laplacian of w. But now instead of the other one up here, we have minus w Laplacian of u. And we integrate that over this volume. That's going to equal this surface integral of u times the derivative with respect to n. That's that unit normal again of w, minus w times the derivative with respect to n of u. Now we integrate that over a surface. Now again, what you should see here is that you see some differences here and some differences here. Again, this is going to come into play where we need to do some proofs. And we're going to say, okay, if you assume one particular thing is equal to 0, then the other thing is going to vanish, or we can set, for example, if this side is 0, we can set this one equal to that one. If that side is 0, we can set this one equal to this one, and things like that. So we're going to be able to use these identities for proofs. Volume integral, surface integral. Again, don't need to memorize these things or anything like that, but they're going to come up again when we're talking about potential fields. Okay, I think that is all for this video, and I will see you in the next one.